Kia ora and welcome to this video on question 3 of the 2020 School Calc exam. There are 4 parts to this question and they're all set in the calculus domain. The first one involves a second derivative of a piecewise function. Part B requires us to find the equation of a curve that meets certain properties. Part C is a related rates question, and Part D an optimisation problem. Okay, question A is actually wrong. The question doesn't work, and I'm surprised that nothing's been said of it, but if we go via the standard ways of solving this and we get the answer that matches the schedule, it turns out it doesn't work. So first up, let's have a look at this. It's a piecewise function which has a parabola on the left hand side of the origin and a combination of an exponential and a sine graph when x is greater than 0. Okay, and it turns out that end point there where it matches, so where the functions meet at x equals 0, is important. We're told that the second derivative exists at, we're given f dash dash of 0 exists. That's the concavity. So we've got some value for the concavity at 0. And what that means is that the curve must be continuous so that it's differentiable. Because if you have a curve that's like that at the origin, so this is x equals 0, if it's like that and there's a gap, then it doesn't have a slope because it's not differentiable. And for it to be differentiable twice, its first derivative must be continuous. Okay, so we start off with looking at what f dash of x looks like. Okay, if we want to find the derivative of it, we just diff both of the terms. So we get 2x plus a for the left-hand side. The parabola differentiates to a line, and we get e to the x plus cos x for x is greater than 0. And we know f must be differentiable so f is continuous. If you think about the parabola and the exponential functions, any value of x can go into those. They're continuous smooth curves, but where it jumps from the parabola to the exponential at x equals 0, it needs to also be continuous there. F must be differentiable, so f is continuous at x equals 0 means that the limit as x approaches 0 from the left must equal the limit as x approaches 0 from the right. Just this notation here, 0 with a little minus over it is saying approaching 0 from the left hand side, from the negative side, and x approaches 0 with a little plus is saying coming from the positive numbers. Okay, coming from the right hand side. So looking back at the first thing, the function, if we make x equals 0 into the function, they should be equal at x equals 0. So 0 squared plus a times 0 plus b must equal e to the 0 plus sine of 0. Okay, 0 squared 0, a times 0 is 0, so we get b equals e to the 0 is 1, sine of 0 is 0. So b must equal 1 if the function is to be continuous. And then we also want the second derivative to exist, f dash dash to exist. F dash must be continuous for the same logic. Okay, so if we now look at f dash, those two functions at x equals 0 must be equal. So we've got two lots of 0 plus a is equal to e to the 0 plus cos of 0. So we get a is equal to e to the 0 is 1, cos of 0 is 1, so a is equal to 2. So b is equal to 1 and a is equal to 2 apparently are the values that make this thing work. But if you look at a graph, which I've already made, you can see that I've got the function in red, and when a is 2 and b is 1, it is joined. Okay, it's smooth, and it looks like it has the same slope approaching from the left as it does leaving from the right hand side. So it looks like everything's happy days, but the black graph is the derivative, and yep, the derivative is connecting, but you can see that it's connecting in a pointy manner. Okay, the slope of the gradient is changing quickly. It's changing from a slope of 2. Remember that the derivative was a straight line, and the green is the second derivative. So the concavity of the original function on the left-hand side of the origin is 2. It's concave up with the concavity of 2. And then straight away on the right-hand side of the origin, the concavity starts at 1 and then gets bigger and bigger as the curve gets steeper and steeper. Okay, so that's a bit of an issue. There's a jump in the concavity. The second derivative is not actually continuous. So what is the value of the second derivative at x equals 0? There is none. In other words, the question doesn't work. But if you put b equals 1 and a equals 2, it seems to me, according to the schedule, that you got full marks for it. Okay, part B. Y equals f of x is a smooth curve over the interval -2, 2 that passes. So what this interval means is -2 is less than equal to x is less than equal to 2. Square brackets mean equals is included. And that's an interval, whereas the second part of this here is a coordinate. But generally speaking, if I had an interval with round brackets, would mean less than or greater than, not including the endpoints. But that's actually a small detail. That's not actually a big deal in this question. We've got a smooth curve in this interval that passes through the point √2, -√2. Given that the normal to the curve, so a perpendicular line, a line that's perpendicular to the tangent, at any point passes through the origin, find the equation of the curve. So you might think about what the curve would look like. If we think about what this curve looks like, the first thing is it passes through this point √2, -√2. Okay, so √2 there, -√2 there. So it passes through this point, and we've got some sort of curve. And we know that its tangent, its tangent is the line that has a slope the same as the curve, but its normal has to pass through the origin. And that's at any point on the curve. So if I take another point on the curve, such as this one, suppose that's on the curve, the normal there also needs to go for the origin. It's a circle, because a circle, the radius is always perpendicular to the tangent. So the curve is a circle, and because it goes through √2, -√2, we can use that to find the radius of the circle by Pythagoras. So we've got √2 there, √2 there, √2 plus √2 squared plus √2 squared, so this is 2. So the curve is a circle, radius 2, centre 0, 0. So the answer to the question is x squared plus y squared equals 4. Now that's not sufficient to prove that it's a circle. Turns out the circle is the only function that has those properties, but suppose that there was another function that always had a normal going through the origin, then we would want to find it. So what we do is think about a specific point on this curve. So I might call this green point in here x naught, y naught. So some point that's on the curve, and I know that at that point the slope of the curve is equal to the slope, the negative reciprocal of the slope from the origin. So in other words, if we have this curve, if y equals f of x is the curve, dy dx represents the tangent to the curve. We know that this normal must go from the curve to the origin, and so like if we were finding the equation of this normal, we would need to find negative dx dy. Negative dx dy is the gradient of the normal. Okay, because two lines that are perpendicular, their slopes will multiply to make negative 1. And we can also find the equation of this line out from the origin, because this distance here is x, and this distance is y. And rise over run would be negative y over x. Okay, so we can actually solve a differential equation, which is negative dx dy, the equation, the gradient of the normal, is equal to y over x, which is rise over run. And this, if we solve this, we're going to be using separation of variables. And this is what you do in integration when you don't know the equation of the curve, but you have a differential equation. So we're going backwards, we've got to integrate. And if we integrate this, negative x, oopsies, that should say negative x dx. So it's negative x squared over 2 equals y squared over 2 plus c, times everything through by 2 and rearrange it. We've got y squared plus x squared equals some constant k, and then I find that constant by subbing in the coordinate root 2, negative root 2, and it gives me k is equal to 4. So there's my circle. So this differential equation, I want you to think about how I actually formed this. I equated the slope of the normal to the slope of the line from the origin out to the point x0, y0. Okay, y over x. It just so happens that y is a negative number, the way I've drawn it. So y over x would be negative. I don't need a minus in front of the y over x. But I needed a negative in front of the dx dy because the slope of the tangent was dy dx. Okay, third question. The rates of increase of the length and width of a rectangle are 2 centimeters per second and 3 meters per second, respectively. So that's dl dt and dw dt. Find the rate of change of its diagonal when the rectangle has length of 12 centimeters and the width is 9 centimeters. Okay, so let's draw a rectangle with a width and length that are variable. So we'll go length, width, and we know that dl dt is 2, and dw dt is 3. They're both increasing, and we're trying to find the rate of change of the diagonal when the length is 12 and the width is 9. So if I call this diagonal here, say x, find dx dt when L is equal to 12 and W equals 9. Okay, so to find dx dt, we need to find x as a function of t. There are a couple of ways of doing this, actually. The first one is to just do implicit differentiation, because we have, so call this method 1, we have L squared plus W squared equals X squared by Pythagoras. And then if I diff these all with respect to time, using the chain rule, 2L dL dt plus 2W dW dt equals 2X dx dt. And now once I've done the diff, I can sub in all the information. So dL dt is equal to 2 and L is equal to 12. So 2 times 12 times 2. W is 9. 2 times 9. dW dt is 3. X, when the width is 9 and the length is 12, the x value is 15. I just used Pythagoras to do that. And dx dt is the thing we're trying to find. So we can go dx dt. We can work out that whole stuff on the left-hand side. And then divide by 2 times 15. We get 3.4 centimeters per second. So that turns out that's actually the answer. It's a very quick way of doing it. Another way of thinking about this problem is to write the length and the width both in terms of time. And so what you could do is say suppose t equals 0 represents time when the rectangle is 12 long and 9 wide. So we'll say at this point in time, we'll just call this time equals 0. Now, the width is increasing at 3, so that would mean that the width is equal to 3t plus 9. Because at time equals 0, the y-intercept of the width equation would be 9, and it's growing at the rate of 3. And then the length is equal to 12 at this point, and it's increasing at 2 centimeters per second, so 2t plus 12. What we can't do is ignore these two numbers 9 and 12 here. We can't just say the width is 3t and the length is 2t. And I mean, if you look back at this dl dt, when we anti-diff this, we'd get L equals 2t plus c. The c is crucial because the width and the length of this rectangle aren't 0 at the same time. This rectangle isn't growing from a point outwards. And it's really easy to explain that, because if we go look at the width of 9, and it's growing at 3 centimeters per second. So that must have taken 3 seconds to get to a width of 9. But the length is only growing at 2 centimeters per second, and it's 12. So that would have taken 6 seconds to get to that length. So it's not possible for them to both be 0 at the same time. So my point is that the 9 and the 12 and these functions are important. And then we use the diagonal. The diagonal, which was x, is the width squared plus the length squared square rooted. And then if I diff, I want dx dt, bring the half down the front, leave the stuff inside the same, to the power of negative 1/2, and then multiply by the derivative of the inner function. And I'm just going to use the chain rule for that. 2 lots of 3t plus 9 times 3 plus 2 lots of 2t plus 12 times 2. And now I'm subbing in t equals 0 into this to find dx dt. And t equals 0 makes a whole heap of this stuff really disappear. So I get dx dt is a half 9 squared plus 12 squared to the power of negative 1/2 times 54 plus 48. So that equals 102 all over 2 lots of the square root of 225. and I get the same thing as before, 3.4. I think the first method is a lot easier when you use implicit differentiation, but you have to know that you can bring in time into these variables L, W, and X, which all depend on time. I've covered that idea in an earlier video. Okay, last question. Find the points on the parabola x equals y squared that is or are the shortest distance from the point 1, 0. There's a couple of ways of thinking about this. We could use a normal, okay, because the shortest distance to this will be one that's at right angles to the tangent. So it's going to be around the point that I've just drawn. Or we can put a point there on the curve, I don't know, call it AB, and then find this distance here to the point 1, 0 in terms of A and B, and then differentiate it. Okay, so if I drop this down here, this distance will be 1 minus A, because that distance is A, and then the height of it because x is equal to a, the height of it will be square root a, because it's on the curve x equals y squared. If x is a, then y is the square root of a, or the negative the square root of a. Okay, so we have from that the distance d is equal to 1 minus a squared plus root a all squared. I could have put b squared there, but then I would have had two variables, and then I'd need to use the equation of the parabola to get rid of one of the variables. Okay, and that's my distance equation. Now, the distance is a positive quantity, and we're trying to find its smallest value. So whatever the smallest value is, call it some value d, that will also be the same value, whatever value of a it is, whatever value of a makes this thing the smallest is going to also make the square of the distance the smallest. So I actually don't need to differentiate this thing at all. I can get rid of the square root. I'm going to show you how to do this. So if I diff this one, I've got d dA, the derivative of the distance function. So I've got a half, because it's a power of a half, times 1 minus a squared plus root a squared times the, to the power of negative a half, times the inner derivative, which is 2 lots of 1 minus a times negative 1, and then the root a squared is a, so that diffs to plus 1, and I'd make this equal to 0. The numerator there, that whole bracket, 2 times 1 times negative 1 is minus 2, plus 1 is minus 1, so we've got 2a minus 1, and then I've got 2 lots of the square root, and I'm just going to tidy up the stuff in the denominator by expanding those brackets to get 2a squared minus 2a plus 1. And I'd make this equal to 0, and a is equal to 1 over 2. A is a half. Because it's this factor here that equals 0. The other factor, the other bracket, this thing here, never equals 0 because it's 1 over something. Okay. Whereas I was saying whatever value of a minimizes the distance, it turns out a is a half, is going to minimize the thing underneath the square root. Because the square root is an increasing function. The square root of 9 is clearly smaller than the square root of 16. 9 is smaller than 16. Okay? So this value of a equals a half makes the thing underneath the smallest, so differentiating the square of the distance also works. So I could call it like distance squared, which is equal to a squared minus a plus 1, and then I just diff this with respect to a. 2a minus 1 equals 0, a is a half. Much easier. The question says find the points on the parabola that are the shortest distance. You must show that your results give the minimum distance. Well, clearly there's no maximum distance, because the point AB, if it was out here, it's way bigger, and it goes off to infinity. So this, because we've got a stationary point and there's no maximum distance, it has to be the minimum distance. We could use a derivative test to prove that as well, but I don't think it's valid. We just say this is a minimum because there is no maximum. So say like infinite distance is possible. Okay, so when a is equal to half, and the y value is either the square root of a, or we can have it down here underneath. So both those positions are the same distance from the point 1, 0. So the points closest to 1, 0 are a half, square root of half, and a half, negative the square root of a half. Just to finish, make a point to show you that we've got the right answer. Okay, I've got the point 1, 0 in there, and I've also got a point on the curve, and I'm making all these other random points. Let's get rid of them. Okay, and then the distance here, AB, is currently 2.36. I can read that off the left hand side, and if I move this point A further away, the distance gets bigger. If I move this distance closer, it gets smaller, 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 smaller. 1, smaller, 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 bigger. So in here is the turning point where and there we go, it seems to be lining up with x equals a half. And we've just proven it. Cool. Catch you in the next video.